Okay, so I'm just going to the content of which we had in the previous class. So we were discussing about, or rather, we started discussion about the coordinate system, the relevant coordinate system, which uh, which is essentially required. So please let me know whether the screen is visible to you or not.
It's visible,
Yes,
sir.
it's visible.
Okay,
Visual, sir.
thank you. So So what we discussed up till now is that we have to, first understand the importance of coordinate system, because ultimately in geoinformatics you are trying to define points. When you are trying to define points on the surface of Earth, you have to know from which reference you are defining those points. So first of all, the coordinate system, which is defined by various geodesists throughout the evolution, and which is at present we are following. This is very important that you should be aware of it. And apart from that, the categorization of the datum, that means horizontal positioning is given by a different datum, vertical position is given by a different datum. So you should be aware of those different two datums. And obviously in understanding that part, which which deals with the coordinate system and position estimation with respect to a reference system in three-dimensional space, and in fact at the same time the in a time varying phenomena, that means their position is changing with time. We are in the into the field of the classical geodesy. And this geodesy domain, it started with this concept of giving positions and uh, doing or measuring the distance between two points. That was that I was talking about the 18th century, and gradually it is evolving from that to in last two centuries. We are working on it and improving our understanding more or less how we are doing it. Gradually, the phenomena of geodesy, that means understanding about the shape and size of the Earth, the gravity field, as well as the geodynamical phenomena. These are the three pillars of geodesy. That means we have to first understand what how we are defining our Earth. That means the size and the shape of the Earth. At the same time, the gravity field, because gravity is one of the major properties of our planet Earth. And at the same time, because Earth is a living planet, isn't it? It breathes, it swells, it rotates, it revolves, spins, everything is happening. So obviously, because of which, and because of the interior of the Earth, there are a lot of geodynamical phenomena is there. Very popular, you are aware of the earthquake, volcanoes, subsidence. These are some of the phenomena which takes place around the year. Glacier flow, ice flow. There are a lot of things. Okay. So because of which your geodesy domain has become a little interrelated with each other, but it has a foundation, that is the reference frame. You have to understand about the coordinate system, because as the technology is evolving day by day, as you are getting to know about new sophisticated geodetic techniques, be it ground based or space based, the more technology is going in an advanced manner, our updation as well as our what should I say, the update in the reference frame is also going and taking place day by day. And therefore a lot of reports are coming from certain body which is responsible for publishing the reference frame. Okay, so we discussed this and in fact this was the figure which we discussed. It's very nice figure, uh, where it is written in the itself that the earth science application, they two are very much correlated, isn't it? That means for any type of applications which is written in the periphery of this planet, be it earth rotation, sorry, be it tectonic motion and deformation, be it you know the ice melting through satellite altimetry, sea level variation, crust response to loading effects, co and post deformation, volcano eruption, everything. It has a primary base as foundation with the reference frame. If reference frame is not properly defined and you are not aware of it, how it is defined, then all these applications are meaningless. It would be a uh, saying that you are working on these applications but without understanding how the reference frame is defined. And because this classical geodesy, which was previously there, which only deals about the estimation of point and defining the points on the surface of the on the surface of Earth, has now grown to modern geodesy, which is nothing but a toolkit of high precision geodetic instruments, be it a ground based or be it a space based. Okay, so all these applications are naturally you should be comfortable with only after understanding about the coordinate system. And not only single coordinate system, that had the coordinate system has to be geocentric of nature. Geocentric means where your center of mass which is coincide with the center of gravity of the earth. So these kind of applications are there for once you familiar with the so called the reference frame, and then these applications would serve the purpose. Okay, these are various type of application which I hope you are aware that in fact monitoring of solid earth. Many times you try to work in these in this area, be it so called tectonic evolution, be it the monitoring of variation of the liquid earth, so all type of applications you work with generally. So the solid earth, the which has we are saying that your solid mass is over that the so called a liquid layer over which the crust is moving. So that becomes the understanding of the tectonic and non tectonic displacement when you monitor the earth. The monitoring of variation in the liquid earth, obviously the sea level rise, ice sheets, okay, the glaciers. Monitoring variation in the earth's rotation. Your earth is revolving and rotating, so your rotation, that becomes the what is the polar motion and the length of the day. These are the very critical very scientific topics where a lot of people are working around the globe. And most probably I would say that in country in India, a very handful of people. In fact, we can count to one or two or three groups where people are working about Earth rotations from polar motion and length of the day. Mostly the US, Canada, and Germans, they are more largely into this field of understanding the Earth rotations. Okay, then determining orbits for scientific application, because a lot of satellites are coming. Artificial satellites are also coming, and for variety of applications, people are using those satellites. And when satellites would be there in the space, it will move into an orbit, isn't it? And that orbit has to be the position in of that satellite in that orbit, which we call it as the ephemeris, that has to be estimated precisely. Only when then you can start working on those applications for which you have launched those satellites. Okay, then atmospheric remote sensing has also played a very major role. In fact, various space agencies, or you could also get the bodies under ISRO, has expertise in these areas where they try to read about atmosphere with satellite geodetic techniques, ionosphere and troposphere. Then the monitoring the temporal variation in the gravity field of the Earth, which is very important because this is one of the major property, and this is also part of one concept which we call it as physical geodesy. That means the monitoring of temporal variation in the gravity by two methods. One is ground-based methods, and other is a space-based method. When we say space-based methods, that means the satellites, with the help of satellite missions like GRACE, GOES, These are the champ missions. These are the missions which eventually helped us in giving the gravity estimations with respect to certain benchmark. Okay. Then the determining position and their changes with time of points on or above the surface of Earth within the utmost precision. That means how well our techniques is there. In fact, if you read any kind of books on satellite geodesy or maybe GPS, if I just start with GPS is a part of satellite geodesy. When I say satellite geodesy, that means you are because the definition of geodesy is understanding the Earth, defining the Earth. So when you say defining the Earth from satellites, that part that becomes the uh, that that part that becomes so-called just a minute. Yes. So when I say when you read any book on geodesy, satellite geodesy, or any book on GPS, then it start with the way you are working on improving the technology, because nowadays people are talking about millimeter level precision. So how come this millimeter level precision has arrived? It is because of the instrument that has played the part. Because instrument development has very much in the revolution, because you could see from your maybe your parents would have worked with the CRT monitor. Now you are working with laptops. So that's how the technology is evolving. So that creates a foundation for understanding that once your techniques are evolving, your precision is improving. Obviously, the major improvement will go to the reference frame estimation. That means the frame will also be improved, and then only this millimeter level precision is. It is not a one-way communication, isn't it? You cannot work with the so-called you know uh, uh, the the kind of reference frame which is required for millimeter precision is only because these advanced techniques which we are having nowadays. Okay. So these are the categorization which we have discussed. Now coming back to this little part of types of coordinate system. So generally there are three types of coordinate system. One is called as terrestrial, another is called as celestial, and another third one is the orbital. There's another time system, but not in the spatial nature. What I'm trying to see is, if you try to see that this is your sun, and your earth is moving around it, understand that uh, planet earth position on the surface of earth. Sometimes what happens, you do not consider the position of earth in the inertial space or in the celestial sphere, or just you take your imagination, just like you are going through a rocket and you are just away from your, this is your position, isn't it? That's how we try to make uh, you know the person who's observer here, who's trying to see our earth, so he will see the earth like this, that earth is revolving around sun, isn't it? It is rotating also, it is revolving around the sun, isn't it? So the observer would need to understand that how the earth is oriented in this inertial space, because once you are out from the planet earth, now you are in quasi inertial space. Okay, you need to understand that what type of forces which are acting over it, what type of attractions earth is facing. So these kind of phenomena you have to understand, because once you are on the surface of earth, you are not aware of any such, because you cannot feel it. Even if you are standing at a place, you will feel that you are at the state of rest, but it is in the case, you know that your earth is rotating. But for that matter, we are not interested, because our whole sole purpose is at the local level. So but nowadays, with the invention, with the application demand, you are moving from that position, that topographical mapping, to various earth applications, isn't it? Earth system application. So what I'm trying to say here is that, so when you are on the surface of earth, that coordinate system or the positions which you are estimating would be part of the terrestrial coordinate system. Okay, because your source or your origin is on the surface of Earth. Okay, when you are away from surface of Earth, you are in the celestial space, then the coordinate you are working would be celestial coordinate. Suppose a star is there, isn't it? Suppose the star is there in this satellite. Let's say this is star is there, and you have to get the coordinate of this star, which is a part of astronomy, isn't it? To getting a coordinate for a star. So if you have to find out the coordinate of this star, you have to go into the celestial coordinate system. So there is a one terrestrial coordinate system where you are on the surface of Earth. Then there is a coordinate system which is on the which is so-called away from you, or in the celestial sphere, which we call it a terrestrial, sorry, celestial coordinate system. Then, if your satellite is in orbit, then you have to work in this only in this orbit only, and the position of satellite in this orbit would be given by orbital coordinate system. So there are three types of coordinate system which we are interested in. One is terrestrial coordinate system, okay, and another is obviously the celestial coordinate system, and third one is the orbital coordinate system. The terrestrial coordinate system, when you consider the that your origin of the coordinate system, that means this is the, let's say this is the coordinate system Z, Y, X, and if you know that this origin is at the center of mass of Earth, okay, it is the center of mass of Earth, then this coordinate system will be known as geocentric terrestrial system. Okay, geocentric terrestrial system. When the coordinate, when the origin of a coordinate system is at the center of mass of Earth. Okay. Second, if you know that this is your Earth and your work, which we generally try to do, the coordinate we system which we are trying to identify or work with is at local level. That means you have established as origin, which generally people do in any kind of survey. Just like if you're the people with the working with the background of civil engineering, they must have exposed to plane table survey, where they try to establish the plane table over a point with the help of plumb bob, isn't it? That plumb bob, which is pointing towards a point, is defined under topocentric coordinate system. That means you are not aware about where Earth's center of mass is, where we are, how it is oriented in space, but in fact you are more interested in your local survey, local topographical mapping, local scale mapping. So at that time you define your point. So let's say you work with a total station, you define total station at a point where you have to start the survey. So that coordinate system is also called as local, but since the origin of that coordinate system is on the surface of Earth for a local level work, so that coordinate system will be called as topocentric terrestrial coordinate system. I hope it is clear to you. Then in the celestial system, although we will not discuss much about celestial now, but there are four type of discussion which is required. That means these are the reference by which you are interested in that: ecliptic, right ascension, R angle, horizon. These are the four ways you can define a coordinate system in celestial sphere. So we will discuss in next semester about more about celestial sphere, rather than just going into the detail right now. So you just need to understand at this point that you have to work with terrestrial system primarily, then celestial, and then orbital also. Orbital are sometimes related with, instead of working with only orbit, the satellite is which is moving in the orbit, your position needs to be estimated in a geocentric coordinate system. Why? Because of the nature that satellite is meant to serve the purpose, isn't it? Satellite is not sent in the space just for some fancy reasons. It has been sent to the space for community, for humanity, for serving the purpose. And whenever you required the data, you need to have the estimation of satellite position in orbit, and that position in the orbit has to be given in a geocentric manner. Otherwise, what will happen? You will be more dealing with the mathematics part rather than serving the purpose. Okay, so the position of that satellite would be given in the so-called geocentric coordinate system. Any question in this slide, because it is very fundamental slide, very fundamental information you should be aware of before moving ahead into the details. You just need to understand what we are trying to say here. Any questions so far?
Hello, sir. Hello, sir. Please repeat. Topocentric.
Yeah.
Sir, please repeat. Topocentric.
Topocentric. Sorry, please say again.
Topocentric.
Okay, so to topocentric, what I'm trying to refer is, suppose this is this is your Earth, okay, but this is your geocentric, where Earth's center of mass is there, but this is your actual topography. This is your surface of Earth. This is your place where you are, and you have to work with your instruments that is with you, and in order to start the work, you cannot reach this point, you cannot access this point of so-called geocentric, but instead you can establish your total station or tripod here on the surface of Earth, which where you are standing. That becomes the origin of the coordinate system which you are establishing. So that is the topocentric. That means the topo surface where you are standing becomes the center of the origin. So how your center origin is defined, that becomes the difference between geocenter and topocenter. How your origin is defined. Okay, the moment you established your total station over this point becomes 0 comma 0 comma 0, and you have to start taking this as a reference for any kind of distance measurements. This is what we are trying to say in the case of topocentric. Okay, so I think it is clear now. We can move ahead. So we are more interested in the four these branches of study, which we are going ahead in terms of studying this so-called geodesy aspect. So one is geometric geodesy. That means that is dealing with coordinate system. Okay, the various kind of coordinate systems. Another is map projections. That means how the position in 3D is projected to 2D. Okay, with considering the various popular the so-called available of map projections. Then obviously we need to work with your so-called the stars, the the space, the objects in the your sky which you are visible in the night. You have to work with it. So that is the field which is called as geodetic astronomy. It's a very popular field nowadays. It has been reduced because various kind of new application has emerged, and that's why, but still it is being useful, and other kind of discipline people are using it. Then the satellite geodesy, which you are, as I've said, various lot of satellites are available, but primarily in the case of the geodesy, we are satellite geodesy. We are primarily working with the very long baseline interferometry. We are working with SLR, satellite laser ranging. We are working with LLR, lunar laser ranging. Okay, and these are the prime techniques. And apart from that, some artificial satellites are also coming, through which we are taking Earth observation. So satellite geodesy is actually being being done just for this purpose. The physical geodesy is all about the Earth interiors, how the interior crust is distributed, the mass distribution, solid mass distribution inside the Earth, because of which the gravity reflects. So the physical geodesy is all about understanding the spatio-temporal nature of the gravity with the help of space-based techniques as well as the ground-based techniques. So these are the prime branches. Okay, and in fact, majority of the community is working in all these five branches. When I say we are working from satellite geodesy, so GNSS is one of the topmost instrument which is popularly people are using. We are call it, this is the popular other name is called GPS, Global Navigation Satellite System, Global Positioning System. So global positioning system is from US, but now other countries have also participated. Russia, European Union, Japan. So they all are coming with their own navigation satellite system. So their parent branch is known as GNSS, which is called as Global Navigation Satellite System. Okay. Then this another part known as VLBI, which is very long baseline interferometry. Another is satellite laser ranging, and then the lunar laser ranging, and then some artificial satellites. So these are the prime branches of geodesy. And the geometric geodesy is all about discussing about the coordinate systems. This is your so-called planet Earth as we see from space, maybe by 400 kilometers from International Space Station. Uh, and it's a very good surface, and it looked like as a sphere, isn't it? As a solid sphere, as you see this figure from space. Okay, but if you come to the reality, your Earth looks like this. So from 400-meter, it looks like that everything is okay. There is no problem. But since we forgot to mention that your Earth is rotating, so the moment we say that Earth is rotating, that means this body is rotating. Okay? This body is rotating, and when this body is rotating, so there is, and this body is nothing but only solid plus liquid. So solid is also there, liquid is also there. That the now your basic physics you could know if you have a bucket filled with water and certain pieces of solid mass inside it, and you put your hand in between that bucket, and if you put your hand in that bucket and you try to rotate your hand such that the water, what the liquid will go, and in this manner it will go inside that the layers of the bucket, the all sides of the bucket, the water will stick to it. And that phenomena, and because of that phenomena only, what is really happening is that your Earth figure looks like this. It's little oblate. Okay, we call it the so-called bulged at equator. So this is your equator, the center part of it, and it is bulged. You know that. So this is you need to understand that this is what uh, the actual figure of Earth is, and this is a model which best fit the Earth. The model which you are observing is the model which is best fitting the Earth. Okay. Any questions? And this is your so-called to realize what it is. This is your India,
4.
which is
India.
so this model,
Then
which
then
we
sir,
call it as geoid. This is the model which we call it as geoid. Okay, this is the model which we call it as geoid. I'm again repeating the word geoid. Okay, and that geoid is nothing but which we also known as a surface which best fit the earth. But how this surface is defined, it is a important question which we need to understand. Okay, how we are defining this surface as geoid, you know, this kind of shape which is represented by just ZFZ Postdam, which we also known as the German agency for geodesy. So they have prepared this figure of Earth with the help of gravity value estimation. How the gravity is varying within the space to space, and how the Earth would look like if we join all these as a smooth surface. So very smooth figure, and but the variation would be represented by certain values. And as you could also realize that you could see that if you see the 3D view of it, you will see that there is a certain variations in the places to places where there is a topography. So obviously this is geoid is nothing but representation of height above certain geoid. Okay, so it is height above certain geoid made in a global datum. So we are just observing the whole earth in a global datum. Okay, so this is a global datum which is known as geoid, global geoid. And what we are seeing, the variation, these variations are known as height with respect to this geoid. Okay, and we will discuss much more about the uh, the the height value which we are interested in, h value, the capital H value, which is with respect to the geoid we are interested in. But gentlemen, we need to understand this is a global geoid. Okay, and many a times we are not interested in working in a global geoid. Why? Because we have to work in our own country, isn't it? Our area of interest is our country. We do not have to consider, while doing the topographical mapping, we do not have to consider the Americans, how the height is varying there, or where is the zero level. We are not interested in that. Instead, every community is free to use that datum. That's why the height, which is defined both at global level as well as local level, and local level prevails because of this understanding that height should be local or national level authority should decide what should be the height datum for a country. And in our case, Survey of India at Dehradun, probably you must have heard of this agency under DST, at an autonomous institution under DST. Survey of India is the whole sole authority for defining the vertical datum inside our country with the help of certain mechanism. Okay. Any question in this part?
Sir, the shape is irregular or spheroid?
No, we are still not focused on the type of the shape. We just need to understand that Earth is not a perfect spheroid, which we just shown the previous figure. Instead, the actual shape is this. This is the actual smooth surface. Okay, it is not a category. It doesn't fall under the category of spheroid because spheroid is a very defined category. Okay.
So, sir, it can be called irregular shape.
Yes, it is. It could be called as irregular shape. What you need to understand at this point is that what is the purpose of understanding this concept or looking at this slide, which is called as the actual shape of earth. The purpose is very simple. Our objective from the day one and the first slide was simple. We need to understand about the reference system. Just need to understand this part. What our objective is simple, that we need to understand the coordinate system. This is our one objective. But any point on the surface of earth is defined by xyz, and more importantly, the three-dimensional position consists of height also. The height value comes from multiple understanding. One understanding is that if we are working in a global perspective, we need to take up the global geoid. Okay, that height which is coming from an irregular surface, which is, we call it geoid. But geoid can be at global nature and as well as local nature. Okay, so this global nature is presented here. Local geoid is presented by Survey of India, which is our authorized agency to present the height datum. Okay, suppose this is the curve which we are interested in, and we do not have any ways to represent this curve. Okay, so generally, how do we do it? We best fit a line from this irregular shape, and we try to have this so-called uh, the normals, the deviation from this best fit line. That's how we do it, and this line will become the best fit line, and plus we get certain the so-called offsets from this best fit line. This is our nature of job. That's how we do it, isn't it? So in actual global GI determination, this is the principle. They try to best fit the earth with certain set of polynomials. I have just explained with the case of linear equation, y is equal to mx plus c, but in fact a very high order of polynomial is being prepared that best fit the earth among the observation. Okay, and we are more importantly interested in how the offset are there, because this offset will represent the topography. That means that at some place you could see the 3D view, at some place you will see nothing. You would understand how this topography has emerged out of that surface. What is the real cause of it? So that we need to understand. There is another way by you can best fit your earth. This is one case where you can represent your the earth surface. One is by geoid, as I've told you, and it is, if it is not a I would say that it is a physical surface. Okay, and there is another way scientists explain or define the shape of earth by reference ellipsoid. The reference ellipsoid, the reason is very simple, because your so-called earth is a rotating body with have materials like solid and liquid, and it has been a mathematical figure which could define such phenomena like our earth is ellipsoid. And this ellipsoid has three major quantities, a, b, and f, which we call it major axis, minor axis, and flattening. And this is a mathematical surface. So your earth can be defined by two surfaces. One is called as geoid and another is called as ellipsoid. Okay, so scientists are working who could define the surface of who can best fit the earth by reference ellipsoid also, as well as geoid also. Okay, considering this, what is what is the difference between these two figures, that is geoid and reference ellipsoid, is that the reference ellipsoid is a mathematical figure, geoid is an irregular surface. Okay, what will happen? Sometimes the geoid will come above the reference ellipsoid, and at some places it will go below to the reference ellipsoid. So what will happen? We can have normals to so-called ellipsoid surface to get this geoidal undulation. So this difference or offset from this surface is called as geoidal undulation. You get my point? So there is a ellipsoid, there is a geoid, because that is actual shape of earth defined by irregular shape. So this is the undulations, which is called as sorry, this is the offset, perpendicular offset with respect to reference ellipsoid, and these offset is called as geoidal undulations. Geoidal undulation you could also understand from this fact. This is the actual topography. What will happen? That suppose you put your hand like on a table, and you put a cloth over it. The cloth will immediately take the shape of your hand. So at certain point your fingers at the end, it will take the shape towards the center part of your hand. But you would realize later on that some of the part is missing. It cannot best fit the earth. Okay, that is one possibility which is always there. At certain places your surfaces which you are defining, which we are calling as reference ellipsoid, it doesn't best fit everywhere. At some places the undulations, because of those undulations, we the representation of reference ellipsoid is slightly deviated. That's why the geoid undulations are measured, they are identified with several types of instruments. Geoidal undulation is also part of understanding the gravity of a particular region. Okay, so suppose this is a global geoid. Okay, so you could see from this global geoid the variations which are given, and this is a very nice map which is available on the internet also. You could download it so you can see it. This is the global geoid value, where the geoid anomalies are represented from -105 to, this you could see from -105 to 87, and you could see your value of India somewhere lie between blue zone. Okay, so these are the global geoid which is available. And there is one student which at some point he discussed about Ezium 08. So Ezium 08 is one of the geoid model published in 2008 and still being used. And recently in 2020-22 we'll be having new geoid model. But this is the way you can see the whole topographical distribution around the globe. Okay. This is a very good picture, which is you first try to have a look. This is the geoidal undulation. This is the geoidal undulation that has been prepared for our country, and you could realize from this fact that the contours are prepared at 2 meter interval, and from coastal boundaries to up to Himalaya, the contours are prepared. The density of contour, that means nearness of one contour to another contour, represents the topography, the height variation. The density of contours at one region is representing the topography, and that's why it is in at one region on near Nepal. you could see that topography is heavily varying. Large topography is there, and in other region of the country, we do not have such steep topography. These are the geoidal undulation. I am again repeating. These are the geoid undulation. So right from at the bottom, you could see from at near Sri Lanka, you will start from 100, and then you move up towards the center part of region, which is having around 56 or 60, and then you go on to the top till you have the large variation in the geoidal undulation. Up to 26 you can reach. So there is a value which you could probably understand from that part. So you can understand from this fact that there is a one region called Hyderabad and the Vishakhapatnam. The distance between Hyderabad and Vishakhapatnam is around more than 500 kilometers, let's say. But the topography is not varying, so you do not have much variation between topography from Hyderabad to Vishakhapatnam, which is on the coastal side, and you will have variation of about 2 to 4 meters only. But when you move from Hyderabad to Bhopal, which is again near about more than 500 kilometers, the variation is of more than 10, 12, 15 meters. So this is representing how our topography is represented as part of geoidal undulation. Okay, so this is one very beautiful picture depicting how the Earth is defined, how the geoidal undulations are defined, and how it is relevant in terms of understanding the topography. Okay. So definition of geoid is very much important. I'll pick one by one. You should be following me. So considering the definition which is being given at the 1828 by Gauss, so geometric surface of the Earth which intersect the direction of gravity at right angles, from which the surface of the world ocean is a part. Now just see the definition of geoid. The geometric surface. That means this is a geometric surface of Earth which intersect the direction of gravity. So everywhere, at every place, you will have a direction of the gravity, isn't it? Which is represented by plumb bob. And plumb bob is nothing but is a device. I'll not discuss the plumb bob how it is look like, but it is a accessory part of any instrument which represents the direction of gravity. Okay, that plumb bob is showing the direction of gravity, and the way it intersect with the so-called the surface, which the way it intersect with the direction of gravity at right angles, it defines that geometric surface. Okay, and from which the surface of world ocean is a part. I mean, it is extended in a continent. I mean, you have a ocean surface that is extended, let's say, to a continent, and that is also intersecting the gravity at 90 degree. That becomes the geoid. Another definition which is given in 1873: geoid is a mathematical surface of Earth and the best approximation of the MSL. Now, why it is called as mathematical surface? Because you can estimate the MSL, which is mean sea level, and that's how you can give an example of geoid as by with the help of mean sea level. Then in 1979, it is called as non-hydrostatic geoid is the shape that the Earth should have if gravity and rotation were in equilibrium. It's a then Torch. It's a very good book on geodesy, about the physical geodesy by Torch, and it is a I mean, it's a very basic book on physical geodesy. It says that about 2/3 of the Earth's surface, which is ocean, approximately coincide with the geoid, and the rest continents can be easily referred to it by leveling and gravity. It's the best definition. I mean, comparing it with the literature, we generally follow this type of definition in our literature for defining the geoid. Again, I'm repeating. It is saying about 2/3 of the Earth's surface, which is ocean, approximately coincide with the geoid. Okay, the rest continents can be defined easily or referred easily to it by leveling and gravity. In fact, you must know that that's how we are defining our vertical datum in local scale. When I say local scale, that means I am talking about the country level. Okay, in country, your geoid is actually referred from the mean sea level by the tide gauges installed over coastal region of the country, and with that understanding of mean sea level, we generally transfer the benchmarks to various places of the uh, India. The process called is leveling. Okay. Then there is a very recent definition in 2017, that is, the geoid is the equipotential surface that most closely coincides with the undisturbed mean sea level and its continuation through the continents. Disturbances are caused by ocean tides, streams, winds, variation in salinity and temperature, etc., of the order of plus minus 2 meter. And that's true, in fact, because nowadays, with changes at climates, your gravity fields, attractions, the gauges, the tides are there in the ocean. So geoid is primarily is defined as a equipotential surface. In fact, if you talk about the lakes, Nainital lakes, let's say you have, or lakes in Bhopal, lakes in Chennai and Odisha, the lakes which are not moving, they are stable. That becomes the example, classical example of equipotential surface, because they are not moving. Okay, they are not moving. Similarly, it is assumed, or scientifically it is expected, that your mean sea level should behave as a equipotential surface. But in reality, what happens because of these processes, that means the tides, the stream, winds, variation in salinity and temperature, that stability is not maintained, and because of which there is a variation in geoid, and that variation is also called as sea surface topography, and that topography SST is of the order of plus minus 2 meter. These are the evolution of definition of the geoid. So again, you must realize that there are two types of surfaces by which you can represent your Earth. One is called as reference ellipsoid, and another is called as geoid. Okay, reference ellipsoid is a mathematical surface which is defined by major axis, minor axis, and trying to best fit ellipsoid with the surface of Earth. Okay, in the case contrary to it, the geoid, which is an equipotential surface, okay, that most closely coincide with the undisturbed mean sea level, however, subject to variations. So let's say this is one best example of geocentric and locally best fitting ellipsoid. So what do you mean by best fitting ellipsoid? Locally best fitting ellipsoid means the ellipsoid which are best fitting at a particular country. Obviously, the moment a reference ellipsoid is best fitting a country, that means it has been prepared by local authority. However, the geocentric ellipsoid are the one which best fit the whole Earth. So the red one, which is having a geocentric reference ellipsoid, and obviously you would have the geoid, which is nothing but the equipotential surface, and then you will have the topography over it. Okay, so there are three stages. Let me just again redraw it so that you most of you would follow. uh, okay, so this red one, this one is ellipsoid, this blue one is your geoid, and this is the topography. Okay, topography is also present, which is because of which you have to explain your points over the surface of topography. So this is the place where your the so-called the 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 ellipsoid, locally ellipsoid. This is your local ellipsoid because it is center of mass is shifted from red one. So this is your the red one is your global geocentric system, reference ellipsoid with global geocentric origin, and this is a local ellipsoid with a slightly shifted origin. Okay, so there are two coordinate system here corresponding to the two ellipsoid, one globally best fitting and then locally best fitting. That locally best fitting, let's say this is your country India, and it is best fitting here only. That means it is serving the purpose for local level. It doesn't fit for global purpose. Okay, and coordinates of one coordinates in local ellipsoid can be easily converted to global ellipsoid with the help of the so-called these factors: translation, rotations, and scale. You can convert between one datum to another, and this conversion is being done by, there is one popular method called Helmert 7 parameter transformation: 3 translation, 3 rotation, and 1 scale. I'm again repeating this because since you are new to this subject, it may be slightly difficult to understand at initial level. But what I'm trying to tell you that your uh, so-called what should I say? The There are two ways by which you can define your surface of Earth. One is called as ellipsoid, another is called as geoid. The ellipsoid could be of global nature, could be of local nature, which is represented by here. The red one is a global fitting ellipsoid, globally fitting ellipsoid, and black one is a locally best fitting ellipsoid. You could also have the geoid, which could best fit the Earth. And generally, geoid are the equipotential surfaces, which is generally prepared at local level, at country scale. Okay, the purpose was same because you have to have the height reference consistent in your country first. Then you can move ahead for other country. Okay, then the coordinate system is of two nature. One is geocentric for globally best fitting ellipsoid, then non-geocentric, which is for locally best fitting ellipsoid. So you have two different coordinate system. One is red, another is black. One is geocentric, globally best fitting ellipsoid. The black one is locally best fitting ellipsoid. Now a point on the surface of Earth could be defined in both two coordinate system, one in globally as well as in locally. So if considering, if you are talking about the old era where a point is defined in locally best fitting ellipsoid, it can be converted to global reference or a global best fitting ellipsoid by these translations, rotations, and scale parameter transformation. You could see that if you reorient the x, y, z, e of local ellipsoid with respect to the x, w, y, w, z, w of world ellipsoid, you just have to reorient this all these axes and shift so that origin should coincide with center of mass of the Earth or center of gravity of the Earth. That becomes that will only be possible after application of translation, rotation, and scale. Okay, if you have any questions, just this is the time you can ask. Any questions?
Excuse me, sir. Suppose we are following
Yes.
global fitting ellipsoid and local based fitting ellipsoid both. What will be the effect on the coordinate system? Is there any effect on coordinates? It will change? Are the both different or will be same?
See, there are two things. First is, if you have the maps, let's say old maps, which are prepared in a different ellipsoid, let's say with reference to different ellipsoid, what will happen? The coordinate will be reference towards the black one, which is, I must say, from this one, let's say from this one. Okay. But considering that nowadays Survey of India has also changed its datum towards globally best fitted ellipsoid, that means the point which you were having before 2005 will be converted to a new datum. Okay, that point will be shifted towards a new point, and that new point could be easily obtained with the help of these functions, with the help of this translation matrix. Will apply as, let's say, a new point x dash would be x would be converted to x dash with the help of rotation, translation, and scale as a factor. It could be matrices with respect to the angles, how much you are changing the orient. In fact, the matrices are directly available. In fact, there are a lot of softwares which I will share at a point of time that you could install on your PC, and you can simply choose to convert from one datum to another, that you are free from.
Okay, sir. Thank you.
See, this is one table which is representing the local ellipsoid, and you could easily identify there is a name written as Everest 1830. I mean, we were ruled by Britishers, but Britishers were a good surveyor, very good surveyors. But at the same time, the other surveyors at different part of world were also there, like Bessel for the European, Clark, then you have Airy, then you have Krasovsky for Russia. So these are the different ellipsoids, and gradually we led to WGS 84. Okay. So this WGS 84, which is nowadays very popular, although it is not, I would say, I mean, given by the international body. Okay, it is given by the US uh, mapping agency, or you could call it geodetic survey agency. But ITRF is a website which is given by the international body called IERS. Okay, we'll come back to that part. But what you need to realize at this point is that these are the reference ellipsoid which are followed at the local level. Okay, and you could see from this understanding that the semi-major axis for Everest would be something different compared to the Clark one from the Krasovsky, and the flattening is also different. Flattening for Everest is considered as 300. Yes, it is also very much true that majorly the ellipsoids which were locally acceptable were not very different from the global one. It is only the origin which is shifted so that their country specific should be best fitted. Okay. So Everest is the name of the surveyor on which this local ellipsoid was given. Okay. Are you following the content? Because it's very
Yes,
basic,
sir.
but yes, because many a time you are just new to this discipline, so that becomes a little zone of confusion and doubts. But please remember that these are the very much basic that you should be aware of. You cannot work on any advanced domain of geoinformatics without going through these basics of, should I say, the foundations of geoinformatics, which is understanding about the coordinate system, these kind of things. So representation of a point can be given in a two different manner. One is horizontally, you can define a point on ellipsoid, and vertically you can have a geoid representation. That means the horizontally you can have you can take help from ellipsoid, but vertically that means the height information should come from a geoid, because from country to country ultimately the height variations are such that you cannot take a reference from other country for working on your own land of parcel. Okay, and in fact this is very much important that you should understand that what is ellipsoid, what is geoid, how the vertical datum is defined, how the horizontal datum is defined, how could we convert from one datum to another datum. And this is very much important, because this is very much part of your understanding of reading of a map also. If a map is given to you, you should properly first look at the legends section, that whether the datum is given or not, whether the information about the ellipsoid is given or not. Then only you can work on conversion. So the earth, which is an independent handling of horizontal and vertical, obviously by uh, representation of horizontal and vertical geodetic datum by ellipsoid and geoid. You could see from these two figures the necessity why we are going from one uh, separate system for defining the height. Okay, because height is a quantity which, if not defined properly, the whole purpose of representation of a map would be distorted. Okay? We are working in 3D phenomena. We are always interested in 3D values. So with this, I will stop here, and in the next class we will discuss more about the geoid, how the heights are being prepared for Indian continent, and what are the different set of observations which one should understand. And we'll also discuss about the ellipsoidal surfaces more in details, and the geoidal undulations, the deflection of vertical. Okay, and we'll also see the tide gauges which are there in different part of the country, and what are the different types of the tide gauges which are being used. And we'll also see about the certain basic of celestial space, sphere, the sun path, and then the basics of the leveling procedures. Okay, so with this we stop here. Any questions?